Hey guys, today I'm going to be talking about using the RocketCEA Python plugin, specifically the code I developed to help use that plugin to come up with the different thermodynamic variables in a rocket engine for various propellants, various geometries. This code has been super helpful for viewing different thermodynamic variables and performance characteristics for the different designs that we're looking at. So RocketCEA is super helpful because this plugin allows us to really use NASA's CEA data and extract it from the Python code rather than going to the web page and running a simulation every single time we make a design change. So what we have on the right here is NASA's CEA page where we would normally go and enter our data, and what we get is a returned list of values for the single geometry or single propellant combination that we provided. On the code here on the left, what we can do is just make a loop where we can automatically iterate through different designs and see a whole bunch of different thermodynamic variables and performance characteristics for all those designs we provided. So it's been super helpful for saving time and maximizing efficiency for choosing designs that work for us. Um, Here we have the RocketCEA page, which I've linked at the top of this code here. This has been a super helpful page to run through all of the functions that RocketCEA provides. I believe there is a link for all the functions. Here we go. Yeah, this here lists all the functions that RocketCEA provides. And so I've already looked through all of these and really chose the ones that are relevant to us. Um, Most of them are. So that's what I've gone ahead and put into this code here. We don't have to use all the data, but it's useful to have just in case we want to go back and look at it. So this page is super helpful for anyone that does want to go back and look at how RocketCEA works, or if they want to add any functions. So the function that I developed, I won't go into the specific details because it's a couple hundred lines here, but the main function that I have here is called CEA propellant data. And so this takes in the fuel, the oxidizer, the geometry, and the pressures. Geometry here is specifically the contraction ratio. That's the ratio from the chamber area to the throat area, and the expansion ratio. That's the ratio of the area of the throat to the nozzle exit to the throat, usually called epsilon. That's why this is EPS here. For pressures, that's just a vector containing the chamber pressure and the ambient pressure. That's the pressure of the atmosphere, 14.7 psi. So using this, we produce a data frame containing performance and thermochemical variables for all of the um, propellant combinations that we provide. Next, I kind of cleaned it up using this process CEA data frame function. So the output of this previous function was a data frame containing all the data that we want to look at, but it's not clean. It really contains everything that I iterate through. But what we're interested in is the maximum values, usually the maximum ISP or maximum thrust or something along those lines. So what this process CEA data frame function does is takes in that data frame that we've produced and spits out the processed one. So I'm going to go ahead and run this. You can see what that looks like. So this printout here just kind of tells you some of the inputs you provided. I've specified that Jet A and liquid oxygen are the propellants. A list of these propellants can be found in that RocketCEA link. There's dozens of them, so you can choose a different propellant, see what happens, and it's really seamless. It's awesome. I've given it a 500 psi chamber pressure, this exit pressure, and these ratios. And so if I go to data frame here, this is the output. What we have is a really clean output. This really clean output containing the different performance variables and then the different thermodynamic variables split into chamber, throat, and exit. So for example, In the performance variables, we have the OF ratio. That's the ratio of oxidizer to fuel in a mass basis. That based on the maximum ISP that we've identified in that previous data frame, we found that 2.29 gives us the maximum ISP from the CEA data. This provides the maximum specific impulse in a vacuum, the maximum specific impulse in ambient pressure, C star, Mach number at the exit, the thrust coefficient, and then all of these thermodynamic variables, including molecular weight, specific heat ratio, temperature, density, viscosity, heat capacity, thermal conductivity, Prandtl number, which is very important for calculating heat transfer properties on the hot side, enthalpy and entropy. And so from this code, it's super helpful for running through iterations, and especially when it comes to Ragnarok's regenerative cooling design, it's important to have the heat transfer properties, especially on the hot side. And so this is very helpful for getting at least a first order estimate of those values. So yeah, so this is that code. I'd love to answer any questions if you guys have any questions. Um, yeah.